In this video today, we will be discussing the nature of entropy, what it is, why it's important, and how we use it. And there's no better way to start a lecture, a video, than by echoing the words of Richard Feynman. He's a famous physicist who's well known for his eccentric personality, bongo playing, teaching, and work on quantum electrodynamics. He once began a lecture in the following way. If, in some cataclysm, all human knowledge was to be destroyed and one sentence was passed to the next generation of creatures, it would be the atomic hypothesis, which is that all things are made of atoms that are moving in perpetual motion, attracting at short distances and repelling each other at even shorter distances. So today, we're going to be talking about entropy, and we are going to amend this sentence by adding a kind of corollary or a comma to it in order to include the role of entropy. And this is going to be, all things are made of atoms that are moving in perpetual motion, attracting at short distances, repelling each other at even shorter distances, where the complexity and disorder of their microstate arrangements increases in a closed system. Now, what do we mean by this? Well, the big point of this lecture or video will be by the end, you will understand what we mean exactly by this final statement. And as we know, entropy is universal. Well, as we will find out. And hence, if you were to jump into a spaceship and leave our galaxy, or even leave our universe into the multiverse, right? And you would find a few of the rules by that statement we had earlier would apply in all of them. Hence, all things are made of matter, or all energy is conserved. But most importantly, you will find that entropy always increases in a closed system. And universes themselves will always tend to higher entropy, i.e. that S entropy is greater than or equal to 0. And because entropy affects everything, separating all that was, nows, and thens, and no matter what we do or go or escape to, entropy will always be there, guarding the universe from reverse causality and multiverse of coffee mugs, as we'll begin to see. We begin, like all things in science, with a question. Why doesn't my desk ever stay ordered, right? We've probably all been thought about this. Or where does my keys go? Or how come coffee mugs break and don't unbreak? And the answer here is this little thing called entropy. And entropy can be viewed in different ways depending on how you look at it. For example, if you look far away, the Earth seems like a blue dot. If you study close enough, you realize it's an elongated sphere at the hemispheres filled with mountains and continents and so forth. You look even closer and you'll see the liquid magma core at the center, and etc. Entropy is similar in this way, that at different scales, you can find its many faces and how versatile it is. And so we begin with the far away or first scale. And this is the fact that entropy is synonymous with randomness and disorder, which we all kind of know about. But it's also synonymous with energy and heat, right? And temperature, all three of those. In fact, entropy is so important that it takes two of the three of laws of thermodynamics, which is the first law is energy is neither created nor destroyed, right? Another way to rewrite that in thermodynamic terms is that mathematically, as the change in internal energy, which is how you rearrange things, the energy it takes to rearrange stuff is equal to the difference between the heat added and the work it takes to add that heat in there, right? Minus the work. So this is another way to state all this. All this goes to zero. All the energy is always going to be zero. It's neither created nor destroyed, but only transformed into one form into another, i.e. kinetic energy into potential energy or chemical energy or nuclear energy, right? You can only transform things. The second law of thermodynamics includes the statement of entropy, which we're going to be learning a lot, which we'll be talking about today. And that is entropy is irreversible and always increases in a closed system, right? Oops, sorry about that. And then the third law, right, is that a system's entropy approaches a constant value as its temperature approaches absolute zero. and the units. And so here we get to the fact that now we can look at the second and third law a little bit closer. Let's peer a little bit in there, and we see the role of entropy, heat, and temperature. The change in entropy, which is that ds, that d is just signifying a small change, is equal to a small change in the heat added to a system divided by its average temperature, right? And so one way we can look at this, as you add heat and give it a temperature, you have more arrangements and more disordered things get, right? Based on something that may have a lower temperature. So we look at this, right? We add a lot of heat and it's more chaotic, more disordered, whereas something like this is slower because it has less temperature. And so that change in entropy of a system is directly related to that heat added to it. And this rearrangement, as you add more in, you can't reverse the process and get all these in the same exact positions as you had it. And so one really good example is that you could take something like ice or a crystal, and crystal or ice has a low entropy because all of these are kind of stuck in place, right? They're all solid. They don't move around a lot. Whereas a gas like steam, when you boil water, these have high entropy because you've added that heat and that higher temperature, and now their atoms are free to move around and take a different amount of arrangements. And we'll talk a little bit more about what I mean by arrangements here later. And so the second law can be stated as the change of entropy is equal to the integral of dq, which is the change in heat divided by a temperature. And the third law is that entropy is greater than or equal to zero, i.e. that irreversibility principle that goes into that. And so knowing the definition of entropy, and its relationship with heat and temperature, I'd like to derive the change in entropy of an ideal gas. And as we know from our previous lectures, an ideal gas is, well, as it's called, a simplified perfect gas. In this case, we assume all particles are point-like, right, and they don't interact. The ideal gas explains the relationship between pressure, which is P, volume V, and temperature T, and also just the number of moles, the stuff that is included in that, right? And so the equation for the ideal gas itself is derived from three other relationships, or laws, which is Boyle's law, which shows us that the volume and pressure is equal to 1 over the volume is equal to 1 over the pressure, or Charles' law, which tells us that the volume and temperature are related, and then Avogadro's law, which tells us that volume is approximately equal to N, which is that amount of substance in moles, right? And then the other thing we need to know is that R is the gas constant given by this value, and CV is the heat capacity for a volume. And so the ideal gas is given by 1 here. In order to derive the entropy for an ideal gas, we start with remember the first law of thermodynamics, which is that the change in internal energy is equal to the change in heat minus the change in work. The change in work can be written as P, which is your pressure, right, times the change in volume. And then D eternal also can be equal to the number of moles, the heat capacity by the change in temperature. So taking these two together, we can rewrite that dq is equal to pressure times the change of volume plus ncv times the change in temperature. And as we know from the second law of thermodynamics, that dq over t is one way of writing that. And so if you divide t by 3 here, this equation, you get the following relationship. So the change in S, which is that entropy, you can take the integral from final to initial, right? And so this will give you your relationship between knowing your volume and your temperature from initial to final of an ideal gas. All right, so to get a better understanding of this relationship, let's look at an example to help us truly grasp this. So let's assume We assume we have 4 moles of an ideal gas, and it undergoes a reversal isothermal expansion from V1, which is your initial volume, to V2, which is your final volume, where V2 is double your initial volume. So you're expanding it, you're doubling your volume at a temperature of 400 Kelvin. So find A, the work done by the gas, and B, if the expansion is reversible and adiabatic instead of isothermal, what is the entropy change of the gas? So we begin with that work, right? The equation for work, which is going to be your pressure times your dV, which is your change in volume. And we can add in here, so taking the integral of that, recall the integral of dx over x, or 1 over x, the integral of 1 over x is going to be equal to the logarithm, natural log of if your final position minus your initial, and then that relationship of natural logs is just written as the final divided by initial inside the natural log. And so that's where we can write that, and then we can input in there that V2 is equal to 2V1, and from that, we get work is equal to N, your moles, so 4, right? Times the gas constant, 8.3 joules per mole Kelvin, times 400 Kelvin, you get about 9.2 times 10 to the 3 joules. So we can take our relationship for entropy, right, and plug it in there. And since we know it's an isothermal expansion, since it's isothermal, we know that the change in S now can just be equal to that Q over T, right? Not the change, but just the Q. And since it's isothermal, the internal energy is 0. So therefore, heat is equal to work. And we have our work equation that we've already solved for. And so the change in entropy is equal to the work divided by the temperature, which gives us 23.1 joules per Kelvin. So that's an example of solving that. And so let's now look at some of the effects of entropy, right? What it leads to for the physical universe that we exist in. Most specifically is the arrow of time. So all the laws in physics are, for the most part, time reversible, meaning it allows us to reverse time and the law still works. This includes gravity, electricity, and magnetism, the decay of particles for the weak interaction to the interaction of protons and neutrons in the nucleus. So the question is, why do we experience time in the way of past, present, future? Why does it have this kind of linear relationship where obviously the past and the future are different, they're separated? And the answer here lies in entropy. And this is because entropy flows only one way, i.e. the second law is that irreversible part of entropy where the future has more disorder or is more disordered than the past. And we call this the arrow of time. So entropy is almost like a filtering mechanism where once you put it through here, you get this separation of past, present, future, which is what we experience on a classical level. Yet we are bound by time. And forever, as Nabokov said, stuck between those two eternities, right? Between life and death. And by this, we're also stuck between a causal structure of reality, meaning causes precede the effects on our level of things. So motion occurs because of force overcoming the normal and frictional forces occurs. And that force is acted upon an object, which causes it to accelerate, right? An object does not just accelerate and then a force happens. This is just absurd. And it seems that entropy limits, that absurdity of natural phenomena by making the absurd or impossible things just very, very unlikely. And so if you look at that in a causal way, this is why you don't start by your coffee cup broken and then it just reforms into a full coffee cup. Now, entropy says nothing that this is an impossible thing that can never occur. It just says it's very unlikely. And we'll talk a little bit more about probabilities later, but and hence we can see we start from lower entropy to higher entropy, and which is separating the past from the future. So the other way we can view, and this is kind of the last part of now we're focusing in on entropy even more, is the statistical mechanic nature of entropy, which is its microscopic nature. And so we can look at this in terms of its microstates. And this was first shown by Ludwig Boltzmann in 1877. He showed that entropy is nothing more than the logarithmic statistical disorder of a system, where that W here is equal to a microstate. And so this can be an energy of that a particle can be in, or its position and stuff like that, right? These are the available energy positions that it can be in just based on its temperature and based on its heat, and just available based on its energy levels. And so one way we can look at this is that at low temperature close to zero, S, the entropy is very low. And so these two little particles can only sit in this box. But as we increase temperature, now these particles can go in other boxes, right? And so they can have different combinations. So let's say we increase the temperature even more, giving it more boxes to be in. So now these particles can take all types of different arrangements, right? And so S is going to be equal to the Boltzmann constant times the logarithm of these microstates. And so microstates are just different configurations they can be in. And all microstates are equally probable. And one way we can write this is in terms of factorials, which will give us our complete number of arrangements based on n particles and put into small n different combinations. And remember, the definition of a factorial is over here. And so this here is really the ontological meaning of entropy at the lowest level, right? At the lowest level, entropy is nothing more than the number of microstates an object can be in, given a certain amount of energy or position, right? The more energy you add to it, the more boxes you have for different arrangements to be in. And remember, as the third law said, as we go forward in time into the future, this number of microstates keeps increasing. And you can even think about it in terms of the fact that, the universe is constantly expanding and you have more states it can be in. But the more states it can be in, it's most likely going to take an arrangement, a probabilistic arrangement of being in the most disordered state. So hence we go from something where this is nice and ordered to now these particles everywhere. And this is a picture of Ludwig Boltzmann, and he obviously has his famous entropy equation right there on his gravestone. And so a good example is that to grasp kind of numbers, and what we mean by this is that let's you take a box of 10 particles, right, which has a partition separating the two. So this is that partition, and you have N1, N2, N1, N2, because these are the left side and right side of the box. And we can calculate the number of microstates for the combination of equal number of 5 per side of the wall, right? And so here we have, this would be the equation, Boltzmann equation written for, we have 10 particles, 5 on the left, 5 on the right. So this gives us about 3.6 times 10 to the 6 different combinations. And then we can write as the entropy of 5.5 times the Boltzmann constant. Now, this is a very likely scenario that all the particles are evened out between each part of the box. Something that's very unlikely, is that all 10 particles are in the small corner of this left side of the box, which is unlikely. When you go into a room, right, all the particles just don't get sucked into the top of your ceiling, right? That doesn't make any sense. At least that's not something we experience every day. And so writing this would be that we have 10 particles, and it's all 10 on the left side and 0 on the right side, which would give us a 0 for our entropy. So, and then one way of kind of grasping just the statistical significance of this is, let's say you had 100 particles, and you would find that this arrangement here would be 1 times 10 to the power of 29. That's 29 zeros times more likely to occur. And if you were to assume a new orientation, i.e. the particles move around and create a new orientation every nanosecond, it would still take you 5 times 10 to the 12 years, which is 750 times the age of the universe, to ever find a microstate in this position, right? That's 750 universes to ever have them all into that one side right there. Now that we have kind of an intuitive grasp on the nature of entropy, And as I said earlier, entropy is not only versatile, but it's everywhere, including physiology and biology. The reason for cellular death lies in the nature of disorder and entropy. Hence is why we use cryogenics to reduce the entropy of a system so something can live longer, right? Because you're reducing the entropy of it. And one way to look at this is that the reason we die is because the proteins inside of our cells are decaying. And by decaying, what we're talking about is that the proteins inside the DNA are folded, right? They are folded in there, which has a very low entropic state. It has a low entropic state because it can only be folded a certain way. Whereas the unfolding process, this has a higher entropy because it can go into many different states because there's an infinite different ways, right? You can, maybe not infinite, but a large number of different ways you can unfold it, whereas there's only a certain ways in which it can be folded. And this is what causes you to age, right? For things to start breaking down is because of entropy. And so the idea of longevity in medicine was that maybe one day we can have nanotechnology that keeps these proteins folded, and hence we can live longer. But regardless of that, we'll never be able to defeat it because entropy is honestly the law of the land, well, of all lands and times. But you also may be wondering, based on the third law, where I said that entropy approaches zero as the temperature approaches zero. Because if you have absolute zero, which is 0 Kelvin, then there's only one available microstate, right? For everything in the universe, there's just one particle. That particle can only be in one state. So technically, entropy can go to zero. We can beat that. We can live forever. And this might be true classically. However, here comes quantum mechanics, right? Quantum mechanically, even the zero order energy states that there is still some energy there, right? If you're looking at a harmonic oscillator, there's a 0 point energy in which we still have an amount of H frequency. So the particle's still vibrating. And by Heisenberg's uncertainty principle itself, it states that the uncertainty position times the uncertainty momentum is greater than some value, right? And so these are complementary pairs. And so if I have knowledge of one, I lose the knowledge of the other. Another way of writing this is that if we did approach 0 Kelvin, we knew exactly the position of the particle because it's not moving around. We can also write this as momentum as v times the velocity root mean squared. If we know from the ideal gas laws that the energy of the kinetic energy is going to be equal to 1/2 mv, that RMS squared, which is also going to be equal to 3/2 that Boltzmann constant times the temperature, which then we can write as VMR squared, that root mean squared velocity, as a function of the temperature. And hence, if we know exactly where that particle is, then we have zero knowledge of its momentum, or in other words, its root mean squared velocity or its temperature. So hence we kind of hit ourselves in a paradox, right? Which again tells us that quantum mechanics will never, ever, ever, ever be able to approach that 0 Kelvin. There will always be a little bit of energy or a little bit of heat or a little bit of temperature there. And so we'll never be able to escape that increase in entropy. And so between our eternities of life and death, there is entropy. It's guarding our universe from reversibility, right? And entropy is the cause of increasing disorder, and it's the heat death of the universe. However, it is also the reason for the complexity and the impermanence of all ontological forms you see in the universe, because nothing is still. Here, entropy separates the past, the present, the future, and the nature of causality. And if we ever hope for immortality, entropy is the true reaper that's holding us forever in this uncoiling, immortal double spiral of life. And if it wasn't for entropy, you could watch this lecture in reverse and get the same information understanding. But sadly, this lecture also holds to the principle of irreversibility caused by entropy. Thank you for listening, and perhaps next week we will discuss the nature of the wave function in quantum mechanics. And here are some problems you can look at and books and other references. Thank you.